Hello, everyone, and welcome to today's webinar, Using Open Source and Built-in Tools for Supply Chain Validation. My name is Melissa Russell, and I'll be the host and moderator for today's session. Before we begin and do introductions, I did want to do a few housekeeping items. We are recording this session, and we will be making a copy of the slides as well as the recording available probably in the next day or so. If you do have any questions, please feel free to go ahead and put them in the Q&A box, and we'll take some time at the end or possibly be able to address some of them in real time here during the session. At this time, I'd like to go ahead and introduce our presenter, Paul Azadorian, who is the Principal Security Evangelist here at Eclipsium. Paul, please go right ahead.
Thanks, Melissa. Thanks, everyone, for joining today. So we'll be covering a lot of like hands-on tools, tips, and tricks, even some hardware stuff that's based on a blog post that went off to our Eclipsium blog today on using the Bus Pirate 5. So I'll cover some like additional things that I had on that post, but most of it will be hands-on technical stuff, and I've got a little bit of information to kind of tie it all together in the end on how you use this information to validate things in the supply chain. So I'll just go ahead and get started and dive right into it. And I wanted to talk first about how many devices are in your devices, right? It's kind of like that exhibit meme that we all know and love, I'm sure. Like I like devices so much that I put devices inside of your devices. And I still think it's staggering to me today to dive into what all the different components are in our computing devices today, and knowing that each one of these components, both hardware and firmware slash software, also has its own supply chain. And so when you look at the average desktop today, as an example, laptops and desktops are represented by approximately 265 different suppliers. There can be, over 40 different components that are running some kind of firmware or software inside of your systems. And if we look at some of the major categories of those are, of course, your CPU. Inside of your CPU, if you're running from Intel or AMD, has an equivalent. You have a management interface or subsystem that runs firmware called Intel ME if you're running Intel processors. We also have network cards, BMCs, baseboard management controllers that can be inside of typically your servers. Of course, we have the BIOS or UEFI, which I'll spend some time talking about today. You do have various other embedded controllers, which we have seen some security research on some of those embedded controllers that go typically inside your laptop to control things like your keyboard, the lights that illuminate your keyboard and your volume buttons and things like that. And then more traditional things such as your RAM and memory and SSD. I will dive a little bit into some of the storage things. I've got some additional information I added just for this presentation on some storage devices. I should also say that all the commands that I will show today, again, you'll get a copy of the slides, and we also have a set of cheat sheets for Android, Linux, and Windows systems. And all of the commands are either in those cheat sheets as we've published today, and there's links to them. And towards the end, I'll talk a little bit about some of the work we're doing to formalize some of those cheat sheets and maintain them going forward. And so again, these are all commands that you would run to obtain information about your hardware, firmware, or software. And then it's a process after that to do some level of validation against that to know if you're running the right things, for example. So who attacks this various pieces of firmware? And largely, with this slide, I stuck with UEFI firmware. We do have published on our blog the attack timeline of various malware campaigns and pieces of malware that are known to attack the UEFI or firmware layer. And there's, of course, a rich history of all of this malware. Recently, the most recent example that I could find was Globteba, which is a older malware family or a piece of malware, if you will, that recently added some bootkit capabilities. And again, the trend that we've observed for some time that I believe is increasing is an increasing spotlight on attackers going after things such as firmware, and specifically going after things such as UEFI or your BIOS inside of your computer. And these various malware families are adding capabilities to persist inside of this firmware to use this layer underneath your operating system to gain elevated privileges within your operating system. So knowing all that there's multiple components inside of your computing devices that all have complex supply chains, and that attackers are digging into this attack surface, if you will. Some of my work recently has been uh, arming people with the commands and knowledge to go, well, what BIOS am I running? What firmware version am I running on my storage device? So we'll walk through several examples of commands you can run that are free and or open source. So either these are tools that are included in your operating system. For Windows, as an example, which I won't spend a ton of time on some of the Windows stuff because I'm more of a Linux person, so this will be very Linux based. But a lot of the tools are included in things like Windows, such as PowerShell libraries that you can use that are built in to interrogate your system, as well as several different Linux utilities. I won't cover too much on the Mac OS side. We haven't done a lot of work to arm people with some of the things you need to do on Mac OS. It is a very closed and proprietary system that Apple provides, which doesn't mean it's any more or less secure than anything else. It just means it's a very closed and proprietary system. And so I think some of the next work we might do is to be able to replicate this work that we do on Windows, Linux, and Android for the community, and perhaps have some things that are appropriate for Apple hardware. But again, it's a very closed system, so it's hard to gain some of that visibility and then validate those results when in a such closed system. So the first thing that we need to address, I believe, is checking your BIOS or UEFI version, right? Am I running the latest UEFI BIOS for my computer? And so this is, a very basic thing. It's been around for a really long time. Many of us may remember, if we're older, like myself, you used to have to put a floppy drive in and a floppy disk in the floppy drive and boot up on that in order to update your BIOS. Things have evolved since then, and the update process is, of course, now very dynamic. And from the operating system now, we can query what version of UEFI that you're running. So in Linux, there's the DMI decode command, which you can use to then get the version of the BIOS that you're running. For Windows systems, you can do this with WMIC, and you can see the command there. You can also use some PowerShell commands, which I have later on in the presentation to do that as well. And there's some links to resources there. Now, again, you have to go in and this will get you the version, and the second command there will get you the release date. It's then up to you to manually go to the manufacturer and go, well, which version should I be on? Is there an update for it? So, a lot of it is recognizing what firmware you have, what version it is, and then go doing the manual update. And it's kind of a tease for our platform, which I won't focus on for this presentation, but our platform automates some of that for you in telling you that you're out of date and even allowing you to apply updates through our platform to do it. But I want to raise awareness about how you can go discover some of these use cases about what's out of date in your environment and then manually go apply these updates. So very first basic thing, check which version of UEFI you're running. Now, the next thing that was introduced into UEFI, obviously several years ago and became a standard on most PCs today, is secure boot, right? That process to validate the software that's included in your boot process from very early stages of the boot process all the way up into the operating system and kernel, and even operating system drivers can be validated using the secure boot process. And so secure boot is a great mechanism, as just it's there to protect. Usually if your IT department has provision systems, they have secure boot enabled and it's there. But we can use secure boot on our own as well as a validation process for what's running on our systems. So it very much speaks to identifying issues in the supply chain. If something's been tampered with or is vulnerable or has been revocated from the list, of known good software that can be used in the boot process, that's Secure Boot's place in our IT environments today. So a quick overview, Secure Boot uses a hierarchy of keys and key stores on your system in order to validate the software and or firmware that's involved from the early stages of UEFI, again, all the way up into the operating system. So typically you'll have the top level hierarchy key, which is the platform key that comes from your platform manufacturer. And typically you only have one of those, although, it depends on the entire build process, but that's the top level hierarchy typically provided by your OEM. The next level in Secure Boot is the key exchange key, and there can be multiple key exchange keys that allow suppliers in the supply chain to provide a key in order to validate software further down in the process. So, your OEM is responsible for the hardware level. Microsoft will typically maintain a key in the key exchange key store in UEFI to then validate software in the UEFI boot process and all the way up into the operating system. Now, this key works in conjunction with two other stores, or they're actually stored as UEFI variables. And those variables are the DB, which is a list of hashes or certificates that represent software that's valid in the secure boot process. And then we have the DBX, which represents a list of hashes or keys that represent software that is not allowed in the process. So if something, for example, as a bootloader, contains a vulnerability, it can no longer be trusted in the secure boot process. Therefore, the hash or certificate representing that bootloader will be added to the DBX. Um, and so we'll spend a little bit of time talking about how this process works on Linux. When we talk about Microsoft Windows, there's also a process for updating your secure boot DBX in particular is the big one. Microsoft is working on an update to update a lot of these keys involved with secure boot and is regularly pushing out updates to the DBX and is very well documented in the Microsoft Windows environment. So the first step is to see if secure boot is enabled on your system and what state that it's in. And you can do this in a number of different ways. On Linux, you can use the FWTS tool to look for the secure boot mode. A more common way is to use mockutil. Mock stands for machine owner key, because independent of the process that I talked about that involves OEMs and Microsoft and operating system providers, you can generate your own root of trust, if you will, on your system and manually sign and do the secure boot process on your own. One of the ways to do that in Linux is called the machine owner key, or mock, and Linux provides several utilities in order for you to do that. I typically don't recommend that you do that, and that's going to depend on your support inside of your Linux distribution as to how you would construct that secure boot root of trust, whether the Linux distribution has done some of that work for you, or you have to do all of it on your own. So that's a little bit of history about mock and machine owner key. When we get to Windows, again, we can use PowerShell and other commands to confirm if secure boot UEFI is enabled or not. So this is one of the first things to check. I do highly recommend that you enable secure boot because, again, it's validating the integrity of software that boots up your system. And one of the benefits is it's validating software that comes before your operating system, right? Again, the attacker's motivations oftentimes are getting into that software pre-operating system so that they can disable security checks within the operating system and disable things that are providing security for your operating system. So first step, check if secure boot is enabled. You can also look for specific vulnerabilities as well. A few years ago now, Eclypsium researchers uncovered vulnerabilities in bootloader, particularly Grub2, and produced a tool that basically automates some of the commands I described before, but also looks at some of the signatures of the software that you're running, such as Grub, and tells you if that version is in the DBX or should be in the DBX. If the version of the bootloader you have has a known vulnerability, this script will tell you about that. Again, this is somewhat older. The boot hole stuff is about 4 years old now. There have been newer vulnerabilities found in various bootloaders, including shim. We have a blog post on our blog that we dubbed shim shady, is what we called it. And shim is the small bootloader that's trusted by the secure boot process and also allows Linux distributions some control over that to add more certificates so that Linux distributions can participate in secure boot. Shim was found to have vulnerabilities, and therefore we have to be mindful of that in making sure that it's patched and updating the DBX so that older versions end up in the DBX. So there are some specific tools out there that look for certain conditions and certain pieces of software inside of secure boot. You can also dig into some of these variables on your own. I just find it kind of an interesting exercise, when you get a system and you either install the operating system or the operating system came pre-installed, what's inside of all of the various variables in UEFI that contain certificates and hashes, excuse me, that implement secure boot. So you can use these commands here to basically pull out of those UEFI variables what's inside and be able to start looking through some of that data. And what's inside of those variables, right, is following the structure that I've described already. So inside of the platform key, right, is ASUS happens to be the OEM that was providing the motherboard. Therefore, their platform key or CAC certificate will be included in the chain. Microsoft also maintains the third-party CA certificate. And the third-party CA certificate is what's used to sign other software that's outside of Microsoft, right? So your Linux distribution. So the third-party CA is used to sign shim, which is then used in the secure boot process. And you can see evidence of that as well, where Canonical will have certificates in the chain as well. So you can manually go through and kind of look at your secure boot chain and make sure everything's good, right? And there's better ways to update this, which I'll get to as well. I just wanted to show some of the manual methods and some of the commands that I've documented for kind of digging into secure boot on your own. So the big question, and I think one of the most important things to recognize about secure boot is that making sure your DBX is up to date, right? So we've talked about all the different stores and certificates and hashes. But I think the most important exercise that you can do is go, is the DBX out of date? Meaning, is the certificates or hashes of known bad software updated on my system? So do I have the most up-to-date list of what software is in the boot process of my system that is going to regulate that vulnerable software that shouldn't be there? So the Linux Vendor Firmware Service is an open source project. It's run by Richard Hughes, who works for Red Hat, and the LVFS, as it's called, is the name of the project. FWUpd is the name of the software that's implemented primarily on Linux systems, provides a facility to do all kinds of awesome things in validating your firmware, but also has a facility to identify an out-of-date DBX and apply an update for you, which is pretty awesome. So again, it's primarily targeted at Linux systems, but it will go ahead and discover all of those components. It'll discover which firmware is on those components. Now, one caveat with the LVFS project is it relies on cooperation from the hardware manufacturers. So a hardware manufacturer has to participate in LVFS, has to give LVFS some data, firmware, hashes, and other things in order to participate so that LVFS can go, you're running an out-of-date version of this firmware. And we know that because we're working with that hardware manufacturer and they also have an update and you can apply this update. So it does not work for every single piece of hardware and firmware that's in existence, but the database is growing all the time. So you can use the FWUpd manager to get updates. It will enumerate everything that's on your system, and you can see there in the list, it also includes the UEFI DBX. Since Linux distributions all do things slightly differently, what I've observed in the past couple of years is the standardization of how you update your DBX on Linux has turned to the LVFS project, and I think that's actually a great thing. I've actually used this process to update the DBX on all of my Linux systems, and so far, knock on wood, have not had any issues. So as you can see, if you use the FW manager command utility to get the devices, it thinks of the DBX as kind of a device, and it will look at the revocation database that's installed on your system, and it will indicate whether or not there's an update available for you. And you can go to the fwupd.org website. You can read about which the updates match the versions that you have locally with the versions that they have in their database to do this level of validation. And as you can see here, when you do the get updates command, it's updating LVFS, so it's getting all list of all the latest firmware and the latest DBX updates in order to compare that to your system. So the important thing in this slide, the reason I updated the circled that version number there is that it was as of like 1.8.5 version of FWUpd that the capability for enumerating and updating your DBX, I should say just updating your DBX, was included in that version. There have been several releases since 1.8.5, but that was kind of the major turning point for when it supported this updating of the DBX. So if you do an update, it will automatically say, hey, like you've got a DBX that according to LVFS was of version 211. Do you want to update that to 217? So it puts its own kind of version numbers on there. But I think does a great job of this enumeration and allowing you to update it. So you go through the update process and it goes ahead and it updates that UEFI variable with the latest list of software that's not approved. Now, the other nice thing that I like about FWUpd is you can run into this situation. I've seen people posting on forums, over the years, asking like, "Hey, I'm applying this DBX update, but I'm getting a warning." And the LVFS project built this into the software that says, "Look, you're putting the latest revocation list on your system. You have a piece of software that the hash of that software is in the DBX update that you're applying. So if you've got out of date software and or vulnerable software that exists on your system, and a good example is your bootloader, and you're going to apply a DBX update that contains the hash of that known bad software, if you actually apply it and secure boot's enabled, secure boot's going to halt the boot process and go, hey, your bootloader, that hash matches the DBX. I can't boot your system. Now it's usually not the end of the world. I mean, unless you've set a BIOS password and forgotten what that password is, you can go into your UEFI BIOS and you can disable secure boot, get things sorted, update your bootloader. And Linux distributions have gotten good about updating the bootloader for you. So a lot of times people run into this situation where they've got USB bootable drives and they haven't updated them in a while. It could impact the booting of those USB drives. I've seen over time as well. But FWUpd will give you a warning and say, hey, do you really want to apply this update? Because if you do, you might not be able to boot your system. So I like having that safeguard, and Richard and team did a great job implementing that. The other thing that I like about the LVFS project is that Richard's built in some of these security checks to not just your UEFI firmware specifically, but a lot of other things about your system that are implemented by Intel chip manufacturers, Intel and AMD. There's security features in here that are implemented by OEMs, and that configuration that has to come together. So you'll see checks in here. If you run FWUpd manager space security, it will do a security check of the firmware that's configured on your system, specifically the firmware that's involved in UEFI and early boot stage processes such as BootGuard and other safeguards on your system. So it does this tiered kind of layered approach where the HSI one is like a level and it's broken down into multiple levels. And it goes through and it enumerates all of these different configuration options. And some of the things on there are like really in the weeds. Looking at your SPY flash regions and the protections on the regions of your SPY flash on your system, things like boot guard and other safeguards. And so that's a great command to run. Again, it's a free tool to evaluate the configuration of your UEFI and low-level systems. It also has some TPM checks in there too, and we'll talk about some other specific TPM checks as well. Now, the other thing, again, very low level, and CPU microcode updates typically come oftentimes with your UEFI updates. Will apply the microcode update on your processor. So your processor, independent of your UEFI BIOS, right? Your processor runs code that's we call microcode that lives on the CPU itself, has a different update process. Again, can be combined. Sometimes it comes along with your UEFI update. And microcode updates are important for not just performance and stability. So a lot of the CPUs will get an updated software update in the form of a microcode update addressing performance and or stability issues, but oftentimes they're addressing security issues as well. And we see this with the whole class of bugs with Spectre Meltdown and the enormous list of speculative execution vulnerabilities that we have. Zenbleed, in my opinion, being one of the most dangerous in terms of giving an attacker the ability to read regions of memory on the system that they shouldn't. And those vulnerabilities are mitigated with microcode updates. So you can see there's this really long Linux command here that you can use to enumerate the version of microcode that's on your system. Doing this manually is really a laborious task, right? Because Intel and AMD both have very different ways to indicate which microcode you have on your system. Usually that version comes in like a hex string, and there's instructions for some processors like Intel, for example, where you can convert that string, then go compare it to a database and see if you have the latest microcode update. So doing it manually tends to be very tedious and very processor and operating system dependent. So like your mileage is going to vary. One of the things I noticed about Linux systems is that inside of the Linux package called Linux-firmware, now there's lots of firmware updates in there from various manufacturers, but inside of Linux firmware, that's typically, again, it's not 100%, but many distributions will use the Linux firmware package, and that package is maintained to contain microcode updates. Um, as an example, I was testing the Zenbleed exploit on my system. I have an AMD system. Zenbleed came out. There's a GitHub repository. I ran a test. I was able to run and see various memory regions, and the attack worked. I updated my Linux distribution, which updated the Linux-firmware package. That Linux-firmware package applied a CPU microcode update for me. And then next time I rebooted, I came in, I tested Zenbleed, and it was fixed. So sometimes, again, not all times, but sometimes in the process that I really like is when the Linux kernel team and the Linux distributions are taking care of this for you, right? They're applying you that CPU microcode update. In a Windows environment, right, typically this would come down through Windows Update, or you have to go to your CPU or OEM provider to get that microcode update. So it's just a little insight as to my experiences, how it worked on Linux systems. And again, it's not always a straightforward process. It's going to depend on the hardware that you have and which operating system that you're using. But for Linux systems, there are ways to interrogate it and ways in which the Linux distros are applying this update for you. Um, One command I really like on Linux systems is a tool called Inksy, and you'll often see this in some of the forums for Linux distributions as an example. When you are on a support forum for your Linux distribution, and like, hey, I'm having this problem, you'll find that there's like a note in the forum to be like, hey, if you're going to ask a question and want support for that, you should include the output of this INCSI command. So we know what versions of stuff that you're running. We know what processor. You can tell it to report the kernel. So INCSI is a generalized command line utility that allows you to interrogate many aspects of your system, hardware, firmware, and software included. And I found it to be a great tool to gather information about my Linux systems. If you run it with these command line options that I have here on this slide, it will enumerate everything that it can about the CPU. Now, I mean, a lot of times it's parsing stuff that's available in, slash proc slash CPU ID, in other, aspects of the Linux internals. But I find it much nicer to run this tool than, run 3 or 4 different commands and parse the results. So INCSI makes it easier for you to determine which processor you have, which version of microcode that it's running. And the other feature that I like is that because it can gather all that information about the CPU, it will tell you about vulnerabilities. Are you vulnerable to Spectre or Meltdown on this particular system? So it will enumerate some of the more common vulnerabilities that are there, which I think is really nice. And what else about INCSI? Oh, so but also applying CPU microcode update patches, I should also point out, as many of you probably know, they can have negative performance impacts on your system. Also, with respects to attacks against some of these CPU microcode vulnerabilities, or attacks against the CPU, is we don't often see them in the wild. I have not observed, and I've asked around and I constantly check in, like, do we really see these in the wild? I haven't seen a lot of them in the wild. Do I think you should patch them? Yes. Do I think you should suffer horrible performance impacts? No. I also believe that out of all the speculative execution vulnerabilities that are out there, if you want a complete list, I'll give you like a quick hack. You can totally use Chat GPT and go, hey, tell me about all the speculative execution vulnerabilities that have come out for, Intel and AMD. It'll give you a fairly comprehensive list, and kind of give you the chronology. So that's kind of a good way to do it. But again, if you have a CPU that is vulnerable to Zenbleed, you can just, Google search for Zenbleed, or plug it into Chat GPT. It'll give you information about it. You definitely want to make sure that you have that microcode update applied. To me, that's one of the most severe ones that are out there. Okay. One thing, and this is just the kind of the beginning of my thinking about how I would validate some of the software packages that are on my systems. And, one of my greatest concerns when it comes to supply chain security, in the context of running a Linux system as an example, is that we run these commands all the time to use our Linux distributions, package repositories to install software, right? And it's hugely convenient. Don't get me wrong. I love the convenience of, I need this utility to do XYZ, and I can go issue some commands or use a graphical interface, but usually enter the commands in, install that utility, comes from the package repo. Maybe it's precompiled, maybe it's not, depending on your Linux distribution. But I'm able to get that software just by running a command, and that's hugely useful. However, I am very concerned as to how we are validating what's inside of that software package. And there's many steps in that supply chain, of course, the XZ vulnerability certainly being a highlight as to how attackers are using that supply chain and attacking it in order to get software that's backdoored onto people's systems, right? And that's my concern when I do an update of all the software in my Linux system, and it updates 127 different packages, all that new software and updates that are coming down. How do I know if that stuff has been tampered with? How do I know I'm getting the actual software that it says that it is? And so I put together some commands that you can use on various Linux distributions in order to check the integrity of your software tree, right? So I happen to run an Arch Linux based distribution on most of my systems. So I use the pack check command, which looks at if you run it in the way that I've displayed it on this slide, right? It goes through and it validates and it says, well, this software package that you have doesn't match the hash that we have in the central repository, and it does some basic checking. The thing is, when you run this, it could be that, for example, one of the software packages that always comes up, it identifies a file that's like a metadata file, and that file always changes. So therefore, the hash of that file always changes. So pack check always comes back and says, well, this hash doesn't match, right? So then you go to the forums of your Linux distribution, and everyone's like, oh no, that's fine. So my point here is you can run these commands, but then you have to go validate the results, right? And that can mean a lot of different things. And even running these commands could mean that something still has a backdoor, and we don't know yet. It could be that the attackers, as in the many cases such as SolarWinds and others, if they control the software distribution, software creation, and the SDLC and the packaging, they can also control the hashes. So all that stuff would check out. So again, it's not perfect. It's something I'm looking at testing on more Linux distros. And defining the process. Still, it's good to get some of these results. Google search around, see if there's other forum information online about those results that you can use to validate it. Okay, so now we'll get to your TPM. Again, another device that's inside of your most computers today, different versions of the TPM. TPMs are configured to do different things to provide security for your system, such as BitLocker on Windows systems. So it's a good place to check if the firmware that runs on your TPM hardware contains a vulnerability, as an example. There's a couple of different ways to do this. There is a GitHub repository that will look for very specific CVEs. So it will look at your TPM, and it's got some smarts that will go, hey, the version of your TPM, you're vulnerable to this known vulnerability that's out there. Has a very short list of vulnerabilities. But again, it's free, it's open source, it's on GitHub. You can run it on your system. And apparently I'm vulnerable on one of my systems. And the caveat here when we start looking at some of this TPM stuff is the vulnerabilities that this script is looking at. And if you run like the DMI decode command, -t is like for type, that's going to give you information about your TPM, including the version, right? And if you go start looking into that and you go, hey, I'm vulnerable, likely you're vulnerable to the vulnerabilities that were disclosed by Quarks Lab last year. And some of those haven't been fixed, right? This is the challenge with supply chain vulnerabilities, is that it requires cooperation to get this stuff fixed. So Yvon Arce actually works at Quarks Lab. He's a friend of mine. He was the founder of Core Security back in the day. And he was telling me the story, kind of the story behind the TPM vulnerabilities, in that they would observe on a system that the TPM inside that system from a various OEM was vulnerable. And they would go to the manufacturer of the TPM and who makes and creates the firmware or gets the firmware from somewhere else in the supply chain and go, that firmware is vulnerable. And they're like, well, that chip and that firmware is end of life. We're not providing updates for it. So then you go back to your OEM, and now the OEM is in an interesting place where they go, well, we want to give you a software update or not, depending on the OEM. But let's just say they want to do the good right thing and provide you with an update for the TPM, but they can't get the update because upstream in the supply chain, they're not supporting that TPM chip. So your OEM may tell you, well, you got to get a new laptop, right? So you can run these commands to enumerate things like your TPM, but you may just be stuck with it until you can update all of your hardware, which to me is one of the worst possible scenarios when we do this checking, realizing that there is no update for a particular component, hardware or firmware, or usually the combination of the two. There just might not be an update, right? And when that situation happens, I like to monitor for changes in that environment because there is no update. It should never change. I do this on some of my systems that have a UEFI system that the manufacturer goes, OEM goes, it's out of service, end of life. So I monitor that to make sure that it never changes, because if they're not producing a UEFI update, it means that for the most part, the stuff that shouldn't change in my UEFI system should never change. If it does, then that's kind of alerting because there is no update from the manufacturer. And you can use a similar kind of thing on your TPM. Stuff's very hard to track, certainly, because again, there are things that should be changing and things that should not, based on whatever system that you're looking at. So, again, you may just be in a spot where you have to update hardware, unfortunately. Okay, your storage devices also contain firmware. I mean, much like all of the different components within your PC servers and laptops, they contain firmware of their own. And storage is one other area. So you can use the command that I put there to get the latest version of the firmware that's running on your storage devices. And the manufacturers of the storage devices will usually provide a firmware update for that. But again, it falls in that bucket of things that are end of life. If this particular firmware has vulnerabilities, are they going to be fixed? Is it going to be supported? On Linux systems, you can use the ls block command, lsblk, to list your available storage devices. Then use the command on this slide to get you the firmware version, and then, of course, cross-reference that with the manufacturer's recommended firmware model, and then updating the firmware on your storage device. Again, it's kind of that answer like, it depends. It depends on which operating system that you're running. It depends on which storage device you have, from which manufacturer has made that storage device. So you're kind of gonna have your own path, right, when you're updating a lot of this firmware on your various hardware components. There's some other NVMe tools also inside of Linux, which I didn't have a chance to put on the slide as I'm just starting to play around with them. That will also enumerate the firmware versions on there. I have read where Windows has facilities for updating your storage firmware, but maybe the equivalent doesn't exist in Linux. So sometimes you have to boot into Windows on your Linux system in order to update the firmware on your storage device. Is a good way to do that if you're just kind of stuck and Linux doesn't provide that facility. And again, your mileage is going to vary depending on which operating system and hardware and firmware that you have. So that's kind of the if you've got a PC server laptop and you're interrogating the hardware and firmware on it using some of the built-in tools. I did also want to talk about if you're able to obtain firmware, whether that's firmware from the various components or subcomponents in your PC, or whether that's from some other device that you're looking to validate the supply chain. If you're curious if there's vulnerabilities inside of that firmware, if that firmware is using some known vulnerable component, if that firmware, for example, has expired keys or use an algorithm or vulnerable libraries to create a certificate, things of that nature, right? You want to look inside the firmware and validate the supply chain, see if it has vulnerabilities. Now, there's a lot of tools that have been created, both commercial and open source, for doing this. However, one that we're big fans of here at Eclipsium is the EMBA project, which is an open source project for analyzing firmware images. So it automates a lot of the analysis of this firmware. And a lot of the different tools and techniques exist, right? Technique and tooling to decrypt the firmware if it happens to be encrypted from the manufacturer. EMBA will I'll try and automate that for you, right? The unpacking of the firmware. Typically, you get one big firmware blob and you have to pull it apart, right? You got to pull out the file system, you have to pull out the kernel and various other components. EMBA will try and automate that. Now, I use the word try because it's not 100%. It doesn't support every single different piece of firmware out there and work perfectly the first time. However, it does a pretty good job. The EMBA team is doing a great job with that. So If you feed the firmware of whatever system that you want to dig into, some of the things that you'll get from Emba are known vulnerabilities, right? Like one thing it'll do is it'll extract the file system. It'll use QEMU to run the binary. Maybe it's an ARM platform, right? But you're running Emba on x86. So it'll use QEMU to emulate the environment, run the tool, get the version number of that tool, and then using its own CVE database that it keeps updated will tell you if there's any known vulnerabilities with it. And so, yes, you could do this manually, but Emba helps automate this, which I think is really awesome. And again, as with any automation, it's no replacement for a human, but it's a great start when you start looking at firmware because it automates a lot of that manual work. And again, it'll look at source code and binary analysis to find potential vulnerabilities using free and open source tools. So if you come across some source code inside of your firmware, maybe it's a PHP application, and then you want to run semgrep against it to see if there's any vulnerabilities in the source code, right? That's something that Emba will do for you automatically, as well as looking at the configuration and scanning for passwords and keys. So it has multiple different mechanisms to identify a password hash on the file system or some kind of key. And then it will actually go ahead and try and automatically crack that password hash. If it finds a hash that it knows it can try and crack, it will try and go ahead and do that for you all automatically, which is great time saver. So some tips, and this is kind of segueing whether you're doing penetration testing or you're just curious if you're bringing a device into your environment and you can get access to the firmware and you want to just run it through. I have some tips for running Emba. You want to build a virtual machine or system and follow the installation instructions and don't try and deviate from them, right? So like in the instructions, it says you should use Ubuntu 22.04. Now I know a lot of us will see that and go, well, I know how to use Linux. Like I can totally use a different distro. Don't do that in this case. My recommendation: use what the Ember project recommends. Follow the installation instructions. Give that system as much computing resources as you can, right? Within your budget, within your means. Emba can take a long time to run, is doing a lot of automated analysis. So you want to have a really, really the beefiest system you can get. I think of this as kind of like your dedicated password cracking rig that you might line up with graphics cards for processing, right? If you're going to have a system dedicated for Emba, and especially if you're going to do it on a regular basis, you want a beefy system. Emba has its own update mechanism as well. Emba space dash uppercase U will allow Emba to update. That's going to update the Emba software. It's also going to update the CVE database that it maintains as well, and a lot of other things with Emba. You will probably want to adjust the default scan template. So Emba's broken down into a series of different modules. Using the documentation on the site, you want to see what those modules do, and then you want to add some to that blacklist. I've got a basic recommendation there for modules that I don't want it to run on a regular basis. There may be firmware where you do want to run these modules, which is fine, but I like to exclude some of the modules that take a really long time, like you really run Yara rules against every single binary and configuration, and that can take a really long time, as an example. So I exclude that module. So that's my recommended list of modules to exclude. And you can get even more if you want it to complete a little more quickly and don't want it to really go deep into the firmware, you can start excluding some of the modules. And again, they're all fully documented on the Emba site. The last thing with Emba is I like to customize my password cracking dictionary. I've got a lot of different password dictionaries, and you want to have ones that are specific to the kind of firmware that you're testing, or everyone has like their own favorite word lists for password cracking. And so in the configuration, you can replace the word list with a word list of your own. Okay. Really quick. Sorry, I thought these slides were before you. They're a little out of order. I wanted to cover Intel ME quickly as well. So Intel ME is the subsystem and firmware that's in pretty much every Intel processor that is produced today. It's been there since 2006. There's been a lot of controversy. I go through all the details in a link to the blog post at the bottom of this slide. But basically, if you've got an Intel processor, you've got Intel ME, the management engine, inside of it, which is running firmware, which needs to be kept up to date, which could contain vulnerabilities, and has very low level access to your computer and all of the hardware inside of it. There is an add-on component if you've seen like Intel vPro, right? That's using Intel's ME feature called AMT, Active Management Technology, which allows for remote access. So it's very similar to a BMC or baseboard management controller, except it comes from Intel. So again, AMT is a feature set that can be included. So on your systems, you want to enumerate, make sure, see what you have. Do I have ME? What version is it? Does it have the AMT component with it? Does it have the active management technology? Is it configured? Is it provisioned? Is kind of another question you want to ask your systems as well. And again, some manufacturers will reduce or customize its functionality. But today, so I'm still calling it Intel ME. The term Intel uses today is CSME, Converged Security and Manageability Engine. Intel makes available a tool that will enumerate the Intel ME subsystem on your processor and tell you if you're running the latest version. There's lots of different ways to do this. Chipsec has a way to check if it's in manufacturing mode, which means the OEM didn't close off all of the things they were supposed to close off in the manufacturing process, leaving it vulnerable to really low-level attacks. Is just one situation with Intel ME. But also, this tool is from Intel and will tell you if you're running the latest version. And again, on Linux system, Windows systems, you can update it using Windows software. Linux systems, typically the process is to boot on a Windows USB bootable drive and then apply the updates to your system. But there has been a long history of vulnerabilities with Intel ME, Intel CSME, and AMT. So making sure those are up to date is certainly something that you want to do. And again, there's been a lot of tools published to enumerate this subsystem on Intel processors. The one from Intel seems to work pretty well, and that's how you run it. The other thing you can do is go right to the hardware, right? And so we just published today my kind of review and experience with this hardware debugging tool that we call the Bus Pirate. So Bus Pirate's been around, the original version, for quite some time. The new version has been in the works for, I believe, like 2 years, and just started becoming available for purchase beginning of this year. So the Bus Pirate 5, again, is this hardware hacking and debugging tool that lets you interface with all different types of hardware and different protocols. So it can do, serial UART communications. It can talk to SPI flash chips and read and write SPI flash chips. So, a lot of times when now we're getting like really into the weeds of hardware hacking and validating firmware, but sometimes you have to interface with the hardware directly. I really like the Bus Pirate 5 platform. The code was ported over to an RP2040. It contains a screen now, so we can see in real time the voltage that's being sent and received on the various pins. We can I don't necessarily recommend that you plug into a SPI flash chip the way I've depicted it there. That is one way, but I'll show you some better ways as well for doing that, because oftentimes if the hardware device that you're trying to validate, right, doesn't provide a software mechanism for you to pull the firmware off to do analysis, you have to interface with the hardware directly. Bus Pirate is just one piece of hardware for doing that. There's lots of other different platforms and hardware and software that work together to do this. This is just the one. Again, this blog post just came out today. It contains my full review and a lot of how-to information as well. So I use it to read a pretty basic SPI flash. It's the one from Winbond. It's a very, very popular DIP8 SPI flash chip. Make sure that you read the documentation carefully and get the correct pinout. If you were to apply voltage to the wrong pin, you're gonna do what we call like letting the magic smoke out, and you're gonna fry the chip. So make sure you read the documentation and are diligent about putting the correct voltage and the correct connectors to the correct pins. One thing is some of the pins require a pull-up resistor, which lets voltage flow to, in a pull-up scenario, lets voltage flow to a different pin. That I had to actually set that when I was reading a SPI flash chip and make sure I set it correctly before it would actually read the chip. And that was kind of glossed over in some of the documentation. So make sure whatever chip you're working with that you read about if it requires a pull-up resistor. And also, don't what I did in this previous slide, again, the barrel connectors on the various pins, it does work, not recommended. Those pins are very delicate. I broke a SPI flash chip in the creation of that blog post. But they do make, so Bus Pirate, the picture that's here on this slide, actually makes adapters for reading SPI flash chips. So rather than connecting to the pins, you put the SPI flash chip inside of this reader. And that's a much better way to do it. And they make a kit available with those 3 different types of readers. My kit didn't come in time. I'm still waiting on my kit to arrive because I didn't order it when I ordered my Bus Pirate 5. But again, there's lots of different options for reading SPI flash chips and lots of different readers that look very similar to that one on different platforms. And definitely do that rather than using barrel connectors or probe hooks on your SPI flash chip. Really quick, what about Android? Of course, the thing that piqued my interest about Android was Android TV devices in particular. And I'm not saying phones are necessarily absolved from this, but Android TV devices were coming pre-owned. In other words, there was malware and backdoors on those systems that were reported for several years. I dug into it, created a post, and then created also a cheat sheet on how to look at Android and determine if someone had tampered with it already. And there's some great tools out there that I've been discovering and using recently. 2 are listed there. They allow you to pull stuff off of your Android device so you can do analysis and determine if someone's been tampering with the supply chain, for example. It's also fun to find devices to test. My friends and social media followers really loved when I posted this little tiny phone that I bought for $40 on AliExpress. I kind of have a problem. I love buying stuff on AliExpress. This one came in the awesome color of like purple, which was really great. I'm working on rooting it and analyzing the Android packages. If you want to follow along at home, there's a link. You too can be the proud owner of a small little Android phone for the price tag of $40. Again, I believe some of the software that's on there is doing some things it probably shouldn't. And I'm still in the process of analyzing it, but people just love when I talk about this little tiny phone because it's really cool. Okay, now the cheat sheet. So we've talked about validation of the supply chain and all different kinds of operating systems, software, tools. Those are all consolidated. So the 3 links on this slide link to the cheat sheets that we've already published to our blog, right? And so these contain all the commands, descriptions of the commands. Now, a sneak peek for our webinar listeners today is that we are in the process of updating all of these cheat sheets and making them available in PDF versions, not only with updates to have additional commands in there, but different ways to format some of those commands as well in the cheat sheet. You can see here, this is the Windows supply chain validation cheat sheet, has some internal Windows commands, PowerShell, WMIC in there as well. And we've got that for Linux, and we've also got that for Android as well. The Android cheat sheet also has a great list of tools that you can use to not only interface with the Android operating system and collect what's on there, but analyze the APK or Android apps that are on there and look for vulnerabilities, look for things like backdoors inside of those apps. And so again, we'll check our social media. We'll be posting those PDFs as soon as we make a big pass at them and add some extra stuff that we've been collecting. So again, the tools and techniques described today allow you to collect the information about your devices. Largely, it's up to you to validate those findings and answer some of the questions. Basically, is this device safe? Is the firmware I'm running, has it been tampered with or contain a backdoor? Does it match what came from the manufacturer, right? Does it contain vulnerabilities, whether known or unknown? Is the software I'm running on my Linux system, does it contain a backdoor? How do I validate this software firmware update before I apply it? Maybe when I went to go download it, someone had tampered with it. I'm actually putting the vulnerable firmware on my system. Maybe it wasn't tampered with when I got it, right? Maybe I'm actually applying that update. So again, these are all things that you have to research based on the collection tips and tricks that I presented today. All right. I mean, that pretty much brings us to time. I do have one question. Retail do include supply chain attack. So the question is, how do organizations and IT professionals respond to mounting threats against retail security, given that there's things like payment card skimmers and the like? It's a great question. I think that one of the things that I didn't address here is the actual hardware supply chain, right? And oftentimes when we look at attacks against retail and attacks against ATMs and payment cards and the like, a lot of the attacks we see today are hardware based, right? And that's super difficult. And yes, there could be software means where you could interrogate the hardware and go, is that hardware have something extra? Is there a chip that's supposed to be there or not be there? But typically, the way you discover those things is physical inspection, right? So we've heard of X-ray machines and having gear go through X-ray machines to look for evidence of hardware tampering. But a lot of the things with retail, payment card skimmers, ATMs, right, are physical hardware-based attacks, which from the software perspective, I think is really hard to detect. The real way to detect it is to lift the covers and look at the hardware, which is very time intensive, labor intensive. Looking into PLC packages. So I've thrown different types of firmware at Emba. I don't think I've done any PLCs, the programmable logic controllers, but it is pretty good at identifying firmware from all kinds of different devices. So I'll have to find some PLC firmware and throw it at Emba and see how it does. And the last question, problems with late loading microcode updates since Linux has been deprecated by Linus Torvalds on kernel.org. I'm not sure what you're referencing in the last question in terms of well, maybe some microcode updates have been deprecated and not included in Linux-firmware, and that's something you have to check manually to see if your particular hardware and firmware updates are included in the Linux kernel. So I will check the Arch Wiki on that and see exactly what's happening in terms of what updates you might get, which ones you might not get. Again, it kind of speaks to that manual process that you go through.
Great. Well, thank you, Paul, again for such a wonderful presentation. I wanted to thank everyone who joined us today. Like I said, we did record the session, and if there were any questions that came in afterwards, we'll make sure to get those followed up on. And we hope to see you on our next webinar, which is taking place on June 13th. We are going to be doing kind of an overview of our product roadmap and product capabilities. So we hope to see you on the next webinar. Thanks again, everyone, and thanks, Paul.
Thanks, everyone.